am Mitakshi, and today I'm going to be presenting Always-On Diagnostics, which is a tool we are developing at Microsoft to improve monitoring and diagnostics on the Linux SMB and NFS clients. So a little bit about me. I am a developer in the Azure Files team at Microsoft, and I work on improving Linux customers' experience with Azure Files. And I also contribute to the development and enhancement of the Linux SMB client. I work with Steve, and I'm also really jet lagged right now. But here's the agenda for the talk. I'm going to start by giving a background, what eBPF is and what motivated us to develop these tools. I'll also provide an introduction to AOD followed by a demo. It would have the installation instructions, and then we'll take a deep dive into the architecture of AOD, and I'll show some performance benchmark, some numbers, and future improvements that are underway. So let's get started. Here are some existing debugging tools that are available on the Linux SMB and NFS client. There's procfs, trace points, utilities like strace, lsof command, tshark, wireshark, and whatnot. And while these are great, they do not provide granular, continuous observability into the clients. So why eBPF? eBPF helps us run sandboxed, event-driven programs inside the kernel context without having to change the source code at all. So whenever you hit a certain hook point, this could be either a system call or a function entry exit on the user space or inside the kernel space, or whenever a trace point is hit, you can execute certain code without changing the kernel source at all. So this diagram kind of shows how the entire process works. You write the BPF program in C, and after that, Clang takes the program and converts it to bytecode. This bytecode is then injected into the kernel using the BPF system call. And then there's the eBPF verifier that runs on this bytecode, which checks if you're not doing any invalid memory access or if you're not running any infinite loops. Once the verifier has done checking your code, the code is then jet compiled for your machine, and then this code is injected to whatever hook point you want. So for example, this process is invoking a certain command, which in turn invokes a certain eBPF hook point. Your code is going to get triggered. So while this is great, this is amazing, there is one problem that comes. It's portability. We know that the Linux kernel is like ever changing. So you might be tracing a structure called A, and the layout, for example, some fields in the structure might get renamed in another kernel release. So how do you take care of that? One way to do it, like how certain eBPF libraries do it, they just ship Clang along with the binary. So everything gets compiled on your machine itself, but obviously this leads to like big fat binaries that need to be shipped. And another way to do it is using BPF core, or compile once and run everywhere. So core is going to stitch together information from various sources, and it's going to modify the object or the bytecode such that it feels like it was compiled for your kernel itself. So how this works is, if you have the eBPF program, Clang needs to have certain extensions that change your program to bytecode, but also record certain relocation information. For example, the type of structure and the name of the type of the structure, the name of the field that you're trying to access, the type of the field that you're trying to access, stuff like that. Once you have this relocation information and you go to a target VM, the target VM needs to expose something called BTF information, which is which stands for BPF type information. It's just a very compact way for the kernel to tell the user space that this is what my structures look like. This is what my memory. This is what the kernel structures look like. And this is exposed at sys kernel BTF VM Linux, this particular file. So this file includes all the kernel types and structure layouts for the target kernel. So what do libbpf library or loaders like libbpf do is they construct the relocations from the Clang compiled object code and the BTF information on the target and modify the object code such that it feels like it's tailor-made for your own kernel. It resolves these relocations so that you have compiled the code on one machine, but you can run it on any machine, basically. So this is how BPF core basically works. So that is what we utilize for writing these eBPF scripts. libbpf is nothing but a development toolkit that provides us this facility. So the new eBPF scripts that we introduced, I presented these at SambaXP this year. But NFS slower is the new one. SMB slower, it traces all SMB operations that are slower than a particular threshold. So it sits right when the request leaves your subsystem on the wire to the server, and then gets the time when the request comes back to the client, and then gets the latency that is slower than a particular threshold. Now SMB VFS slower traces slow VFS callbacks, so it sits towards the bottom end of the SMB stack as soon as the VFS makes a callback to the SMB layer. Similarly, there is SMB VFS IO snoop, which traces IO errors, function arguments at the VFS layer for the SMB operations. The new command is NFS slower, which traces all NFS operations that are slower than a threshold. There are existing NFS implementations, but they hook onto certain NFS operations individually, read, write, etc. But this implementation can trace all operations without having to hook onto multiple functions. So I'm not going to delve into much detail. Please refer back to the SambaXP presentation if you're interested. But the way SMB slower works is as soon as a request comes, in SMB we have a concept called message IDs. All requests are allocated certain message IDs. As soon as the message ID is being allocated in this function SMB2 mid-entry alloc, we store the time of allocation of the mid in a hash map against the pointer to the mid queue entry structure. And then whenever we receive a response from the server, we release the message ID. So we get the pointer again, and that's how we come to the stored structure value. And that structure value has the time when mid was allocated, and the current time is when the mid was deallocated. Subtract the two, and you can get the latency. And all of this event is going to be sent to eBPF ring buffer so that it can be read by the user space handler. So all of this is happening in the kernel space, and once we are done constructing this particular event with all of the information, for example, the session ID or the command name or what the message ID of the command is compounded, or if it's asynchronous, all of that information is packaged and sent to the user space via the eBPF ring buffer. For NFS slower, we hook onto, so right now this can only trace NFS 4.1 commands, at least that's what I have tested. So it stores the slot allocation time whenever we hit NFS 4 setup sequence code path. And we use the RPC pointer to the RPC task structure as the key, and we store the allocation time and some other data that is given by this particular structure. Once we are done with the RPC task, so the RPC task remains around in my understanding until we hit RPC task exit. Once we hit that, we get the pointer again and extract the data from this particular hash map, and we get the allocation time. The current time is the release time. Subtract the two, and we populate this event structure, which has the session ID, the slot number, the the sequence number, the NFS command, etc. And then all of this is packaged and sent to the user space via eBPF ring buffer again. Now, introduction to AOD. AOD is basically utilizes these eBPF tools to provide low overhead monitoring and observability into the NFS and SMB clients. But why AOD? Why did the need even arise? At Azure Files, we have had customers come to us, and I'm sure you guys must have experienced it too, that there are often failures which are transient and difficult to reproduce. So the only way to monitor them is to just persistently observe those failures, and then once we see them, we start log collection. So all of this manual diagnostics are just slow and mostly time consuming. So like this gentleman clearly says, in modern environment, especially with Kubernetes, we need low overhead SMB NFS client-side continuous monitoring. So that's why AOD, we thought of working on AOD. So some stuff about AOD. AOD is a multi-threaded Python daemon that listens to events that are captured by these eBPF tools in its current form. When we ship AOD, it will run as a systemd service, and in the systemd service file, you can provide certain resource limits so that you can constrain the memory and CPU usage of this particular tool. Additionally, you can also provide a specific disk utilization size inside the AOD config file so that it never exceeds your resource quota. And AOD is going to listen to the stream of events coming from the kernel, and it's going to periodically monitor those events for anomaly. And it is going to trigger log collection as soon as it senses that an anomaly has occurred. And AOD obviously has to have minimal interference with the kernel hot path. It should have a low CPU and memory footprint. It should be highly configurable. And we are continuously working on improving all these metrics. So here is a sample config file for AOD. It might not be very obvious right now, but I'm sure if we look at the demo, it'll become easier to understand. So the watch interval second basically means how often is the anomaly watcher thread inside AOD is going to wake up and observe the events coming from the kernel for certain anomalies. AOD output directory is wherever AOD is going to dump its log bundles. So watch interval second 1 means it's going to wake up every 1 second. And then AOD is running in something called guardian mode, which is the on anomaly mode. That means you listen for anomalies and you trigger log collection. There's support for another mode called the observer mode, where you can do just passive log collection. Just start AOD, specify the types of logs you want to collect, and just passively keep collecting it. So yeah, guardian mode, listen for anomalies. And the first anomaly type that we are listening for is latency. So right now, AOD only has support for latency anomalies. But once we get the eBPF tool for SMB IO Snoop, for tracing the error codes, it will be very easy to add error code support as well. Now, type is latency, tool is SMB slower, and then we provide a way to tune or to kind of tune the commands that you would want to track. So there's 3 acceptable tracking modes. First is all, track only, exclude only. Exclude only means track all commands except these certain commands. Track only means track only these commands. And then all means track all SMB commands. And we have a way to tune the threshold per command. So for example, here in this config, we are tracking all commands, and all commands which take longer than 20 milliseconds are going to get flagged as anomalies. But I am okay if the write command takes 50 milliseconds, for example. So SMB write, the threshold for SMB write is going to be 50 milliseconds. So this is the way you can chain more commands here and specify a granular threshold for each command type, and you can exclude certain commands from monitoring or include certain commands only. This is how you can modify the config file. And there are certain actions that we can do whenever an anomaly happens. So right now, we want to collect debug data or information from proc mounts or dmessage, etc. So, and if you want to add another anomaly monitoring, you can just add another key. For example, error. Specify that tool you want to use. For example, NFS IO Snoop, and provide the error codes you want to track. So all of this is just very, very configurable, very, very flexible. If you want to track SMB slower and NFS slower together, you can just chain them in the config file. Now cleanup interval second. This is how often the space watcher thread wakes up so that it can clear old log bundles. Max log age 2, it means any log bundle that is older than 2 days is going to get deleted. Max total log size 0.5. So whenever we hit the disk space limit of 0.5 megs, we are going to start deleting older log bundles so that we always stay within this constraint. Yeah, so that is pretty much the config file. And this is the overall flow of AOD. We have these multiple eBPF programs loaded in the kernel space. SMB slower for tracking slow SMB requests, NFS slower for tracking slow NFS requests. All of them send their events into a shared eBPF ring buffer. It's a common eBPF ring buffer which collects outputs from multiple producers and gives us a nice stream of ordered events. And these events are read by the eBPF user space handler. And these raw C structures need to be shared to the Python program somehow. So for that, there were multiple design ideas that we implemented, and if you want to discuss that, we can take that offline. But the current design is to dump all of it to a shared memory established between the Python and the C programs. So this shared memory circular queue is going to get these raw C structures from the eBPF scripts. And after that, the event dispatcher thread on the Python side is going to wake up, drain this queue, and batch convert all of these events to NumPy arrays. So once we have these NumPy arrays, we push them to the anomaly watcher queue. And based on what the configured wake-up duration is, anomaly watcher is going to wake up, for example, every 1 second, examine these events, and whatever anomaly handlers you have specified, it's going to watch those and trigger, it's going to create an anomaly action, which is composed of the timestamp and the anomaly name if it detects any anomaly. And this anomaly action is going to be pushed to the anomaly action queue, and the log collector waits on the anomaly action queue and basically starts collecting logs based on the particular anomaly type. And the log bundles are stored on disk, and the space watcher periodically wakes up and cleans up the disk if the log bundle grows more than certain configured size. So yeah, this is the overall flow. Let's come to the demo. Okay. So this is the config file that we are using right now. We are tracking latency anomalies. Acceptable count, that means within 1 second, if there are more than 10, it's not visible. Okay. Okay, I don't know how to make it bigger. Is that better? Okay, so I'll just talk through it, I guess. So we are tracking latency anomaly. If the number of commands with latency above the particular threshold grows above 10 within a second, we flag it as a latency anomaly. We are tracking SMB write, and the threshold we have provided is 600 milliseconds, and for other commands we have provided the threshold as 100 milliseconds. And the actions that we have configured is, we want to collect demessage and debug data, stats, and other logs. The cleanup duration, etc., is the same thing that I just mentioned in the config file. Now, after this, let's just start AOD. I'll try to zoom into the thing. So we are starting AOD with log level debug, which means we are going to get some debug level logs. Now we have started all AOD components. Let me try to zoom in. I'm so sorry. So yeah, event dispatcher has initialized. Shared memory has been established between the libbpf side, the C program, and the Python program. And then you can see that AOD has created all these threads, event dispatcher, anomaly watcher, log collector, space watcher, and it has started the SMB slower process with this particular PID. So the eBPF programs are run as separate process. They are decoupled from AOD. And we can see that the queues and the anomaly action handlers, etc., all of them have been initialized. Now, we have started all components. Now we'll try to kill one of these components and we'll see what happens. So we have killed SMB slower. This is the process ID for SMB slower. We have killed SMB slower, and AOD detects that SMB slower has been unexpectedly exited, and it starts SMB slower again. So anytime any thread or any process inside AOD fails or crashes unexpectedly, the main controller process just restarts it again. Okay, so after this has restarted, we also log this failure to syslog, which, it has restarted, and we also log it to syslog right here. And there it is, SMB restarted due to unexpected exit. Now, let's just run a FIO workload. So this FIO workload is going to create some files, do some random and sequential read writes, and we'll see what happens. So right now, we detected 0 latency anomalies for SMB slower, and the max we detected 0 latency anomaly for SMB slower. So we do not trigger any log collection. But let's move on. Yeah, now we have started detecting anomalies. So I'll just zoom in a bit. So we configured a certain threshold for SMB write, but there are certain commands which go over this particular threshold. So we detected 6 latency anomaly events, but our threshold was 10 if we detect 10 of these events. Let me just move on. So we do not trigger log collection here. Let me move on, let's continue. Right, so now in this batch, we have detected 26 anomaly events for SMB slower. So then we start our log collection. We collect output for this particular command, and output is written to the AOD directory. And this is how we start commands, and then all of these anomalies are logged to syslog as well, detected latency anomaly with such and such number of events. So this is why we are running a workload, and we keep observing the events from the kernel, and we keep collecting the logs. Now, once our workload has finished, let's go to the AOD output directory and see what has happened. So these include some previous logs as well, but this is all the logs that we have collected while the workload was running. And now we'll try to extract these log bundles and see the contents. So just unzipping it, these are the contents of the log bundles. And this particular suffix is the timestamp when the anomaly happened. And and then the customers or anyone can share these logs with us, and we would not have to ask them to wait for a repro. This is how AOD works. Installation steps, we have a very, very comprehensive documentation of the architecture, the usage, and how to add your own anomaly event handlers inside AOD. It's all on the GitHub page. And installation steps, you clone the repository, set up a virtual environment, install the requirements, and just run it Python src controller.py. But when we ship it, we are going to be shipping it as a systemd service. So let's move on to AOD architecture. I'll do a very, very high-level overview of the components which constitute AOD. So there's the AOD controller, which is the central controller process that is responsible for orchestrating and initializing all the other threads and processes that are a part of AOD. It is basically responsible for respawning any thread or process that dies unexpectedly, and it sets up the SHM and it sets up the queues for the inter-thread communication, manages the service lifestyle, and whenever we want to shut down the service, controller is the one that triggers graceful shutdown. And after that, there comes the eBPF program. So we have employed a multiple producer, single consumer ring buffer. There are multiple eBPF programs that will keep writing to a single shared ring buffer. And these eBPF programs are going to be spawned as a separate process from the controller. They will attach the requested NFS and SMB code paths. And just to make sure that we do not clog the ring buffer with any extra events, we need to perform maximal filtering inside the kernel itself. So if you are interested in events that are small, that are higher than 100 millisecond latency, you do not want events that are lower than 100 millisecond latency, for example, or you do not want any extra error codes to go to the user space. So we keep the filtering to the max here so that we do not clog the eBPF ring buffer. And there is a common event interface that there is a common event structure that each of these eBPF programs need to construct so that all of this can be sent to the user space. So for example, we have the PID and the command, SMB or NFS command, whatever, when the command ended, the time in nanoseconds, and a union of the metrics. The metrics include latency in nanoseconds or the error code. And then we have the tool name, SMB slower, NFS slower. This is just to, this is going to be used in the further processing steps to kind of segregate the events for each anomaly type. And then we have the name of the task that triggered this particular operation. So there's, like I mentioned, there's one ring buffer to rule them all. There's a pinned eBPF ring buffer, which delivers a stream of ordered events, multiple producer, single consumer construct. And we are going to be using blocking wait on the user space side to wait for the ring buffer events. Now, the kernel is going to send the output, send these events to the eBPF ring buffer, but since the user space handler is waiting for events to come to the ring buffer, it needs to be woken up. But this wake up latency can be pretty high. So what we do on the eBPF side, the kernel space side, is we batch events so that we prevent waking up the user space handler after every single event. So we basically do batching of the events so that maybe, you know, wake up the user space handler after you have collected 256 KB worth of events, for example. That's a very high number, but I'm sorry. Yeah. Now there comes the event dispatcher. This we are entering the Python code now. This is managed by AOD as a separate thread, and this shares the memory with, this has a shared memory queue established with the eBPF user space handler. Now this event dispatcher is going to read raw C structures from the memory and is going to use C types to convert them to memory aligned equivalent Python understandable structures, and we convert all of them to NumPy structured arrays. Now, once we have the NumPy structured arrays, it's all bulk conversion. We push all of it to the anomaly action queue. And the good thing is that all of this is zero copy, completely zero copy. Yep, so anomaly watcher is going to sleep for certain interval, and when it wakes up, it will consume the NumPy structured arrays from the event queue. And it masks the event based on the eBPF tool type. So if you're using NFS slower and SMB slower together, you might want different logic to trigger anomaly analysis, log collection for both of those operations. So you can segregate these out. And this is all just a view of the array, so no copies are happening anywhere. Now, you can have multiple anomaly handlers with custom rules and configured threshold to detect any anomalies. And we are using NumPy everywhere to provide speed, to provide analysis at native C speed. And we do not have to deal with the Python global interpreter lock. And whenever an anomaly is detected, we log that to syslog and push the action, which is shown right here, constituted of the anomaly type and the timestamp to the anomaly action queue. Now, log collector is waiting on the anomaly action queue. As soon as it gets any events in the anomaly action queue, it utilizes Python's async IO framework so that we can concurrently start collecting logs for multiple anomalies at a time. And all of these are bounded by a semaphore so that we do not spawn multiple, we do not end up spawning multiple child process and threads for log collection. So after the log collection is done, we compress these files. And this is how the directory structure going to look like. And Yeah, so basically we are done with log collection. The space watcher is going to wake up every configured time interval. It's a housekeeping thread that will periodically delete old logs and honor the retention policy. That means it would purge the oldest tarballs based on their age, and it ensures that we are confined to the disk space limits that the user has configured in the config file. So all of these components work together to achieve continuous low overhead monitoring. The kernel does most of the anomaly detection work. The user space threads wake up, they are all blocking calls, they wake up only when they have to and do batch processing of all the events that they have received in their queues. Heavy diagnostics are run in separate processes, and all of this is confined under under resource limits. Basically, even under intense logging, AOD is ensured to remain within a small resource budget. So here are some performance benchmarks. We ran these experiments on a D2S8 Azure VM, 2 CPUs, 8 GB of memory. The FIO workload was a 15-minute workload, which included file creation, small random I/O, and large sequential I/O. And with a good config, and what I mean with a good config is there is a reasonable latency threshold, and we are tracking latency anomalies for SMB operations using SMB slower. The CPU usage without AOD and with AOD is mentioned right here, and AOD impact was 3.3% average. It increased CPU consumption by 3.3% on average. Memory usage increased by 1.39% on average. And even with a suboptimal config, like the worst possible threshold, 0 latency threshold, that means you trigger log collection for every single event. Every event is an anomaly. Even with that, the CPU usage was, the CPU overhead was 5.63% on average, and the memory usage remained pretty constant, 1.33% on average. When there is no workload, when there is an idle share or there is a slow workload, the CPU usage increased by 0.08% on average, and memory usage increased by 0.1% on average. We are constantly trying to improve these numbers, so I'll come to the future improvements in a sec. Yeah, so here are some extensions to AOD we have planned. So currently AOD only has support for tracing latency anomalies, but we want to support observation of more events. For SMB, for example, we want to observe lease break timeouts, reconnect failures, and we also want observability into the TCP and socket level statistics. Right now, the anomaly detection algorithm is pretty rudimentary. We are just triggering anomaly detection if there are 10 events that go above a threshold, but we want to move to a percentile-based algorithm. So yeah, improving the anomaly detection algorithm is another thing on our list. Chaining anomalies. So this is an interesting one. For example, if you have hit a reconnect failure, you might want to start tracing certain error codes as well. You might start to looking out for certain error codes. So if you see an anomaly, you might want to start observing for another anomaly as well. So this is another support that we want to add to AOD. Now we also want to, eBPF is good, but anything that executes in the kernel is obviously going to be way, way faster. So we want to integrate support for trace points, capturing information from trace point. NFS does it really, really well, the trace points. And we also want to integrate support for long-running captures. So some observability into the operations that are happening over the wire. So for now, we just do commands that complete within a jiffy. Reading from a file like procfs stats and stuff like that. But we also want long-running captures like probably Wireshark or some equivalent, probably writing our own Wireshark using eBPF. And then we want to add support for observer mode for periodic log collection, so that it happens in a passive way. You don't listen for any anomalies, it's just passive log collection. And we also want to improve the API reference it's good right now, but we also want to make it easier for other users to add support for watching more anomalies. So that is another thing on our checklist. Optimization, there are a lot, but some of them are, one thing that I do not like is that we need to do a double copy of the events right here. So we are reading from the eBPF ring buffer, and the same event is being written to the shared memory. So this is where we are doing a double copy. I don't really like that. Technically, eBPF ring buffer is just a file descriptor that you can read from Python as well. So the next step would be utilizing something called C extensions for Python so that we can read from the eBPF ring buffer directly from the Python code so that we can remove this shared memory and prevent double copying. But again, shared memory is fast. We need to benchmark which of the two C extensions or shared memory is fast and what the trade-off looks like. So yeah, that would further reduce the memory footprint. And another optimization is to use async IO as extensively. Right now we are using it for log collection, but there are places where we could be using async IO more aggressively to simulate concurrency. Then we also want to offload the log compression to a separate thread. Right now it's happening as a part of the log collection process only. And we also want to add fault tolerance and robustness to the space watcher and log compression thread. So if deleting a bundle or compressing a set of logs fails, we want to be able to requeue the same event so that we do not miss anything. I think we are nearly at the end, but I have a backup slide on how to add support for observing new anomalies. So you basically need to create your eBPF tool or take any existing eBPF tool. To make it compatible with AOD, you need to use eBPF ring buffer to send the output to the user space. And you need to use the same shared user space handler to load and attach the kernel space program. And you need to send the output in the common event structure. So all of this is documented inside the API reference and the usage guide. And in the same, like I mentioned, use the same user space handler for all eBPF programs so that we have the true multi-producer single consumer construct. And now in the controller, we need to provide support for invoking your eBPF tool and just add the anomaly handler, basically the algorithm to flag anomalies given your batch of events, and add the log collection handler if they do not exist. And this is how you can just improve support for tracing more anomalies. So, yep, I think that's the end of it. And thank you so much for attending, and I'll take any questions now. Yep. Thank you. I have provided references, I'm so sorry. I've provided links at the end of the repository, the eBPF scripts, and the SambaXP presentation. And I have also tried to link the documentation. We have very good documentation in the slides themselves. So please feel free to browse through them. Yeah, I'm so sorry. Yep, for sure. Like I mentioned, extensions, we want to extend the support for monitoring a lot more events, and this is just needle in the haystack. We can improve observability, and basically I want to be able to capture information from trace points as well, so that thing is also necessary. So I would appreciate community feedback on how to write more tools and what other events we can observe. Yes, Chuck.
So here's some feedback. I love this idea so much so that we actually have our own tool called like data recorder that is always on.
Okay.
Yeah. The problem with our tool is that the main developer retired 6 years ago.
Okay.
So what I'd be interested in seeing is a way of moving this work into the community, i.e. packaging it and making it available in distributions. Do you have a plan for that?
Yep.
FDR is, I believe, it's either in the extra packages for Enterprise Linux repo, or it's in Fedora. I don't remember which. We did that and then we got retired. So this looks like a way of carrying on that work and making always-on observability something that everybody can use and depend on. So congratulations on that.
Thank you. Yeah, and yes, we have all the plans for open sourcing this tool and making it making it such that anyone from the community can contribute and scale it, and we'll ship it on packages.microsoft.com to be available for the community anytime.
And ours does trace points. We did do BPF. I just wanted to share this a little bit. The reason for that is because many of our customers, I work for Oracle, many of our customers are paranoid about inserting dynamic code into their kernels. And so the trace points are actually statically built into the kernel, and so that's what we went with. So I think that's a good direction for you to go in.
Yep. I mean, are people reluctant about executing eBPF code? If they execute, if they run Wireshark on their systems, this won't be very different. Wireshark also uses eBPF, if I'm not wrong, but I understand because there are certain Azure customers also who have certain security boundaries, and we still need to look into those. Trace points, extracting information from trace points is good, but especially for latency, we needed certain code to be injected into the kernel so that we can store the entry and exit time of certain functions. So this was necessary, but obviously code that runs inside the kernel is going to be faster than any eBPF program you write. So utilizing trace points is like it's a really it's like the North Star for us, to improve observability as much as possible.
Well, the right people are in the room to help you add the trace points that you'll find most useful, and make them a permanent part of the current code base.
Yeah.
So one thing I'm curious about is how many of the tools don't depend at all on Clang and eBPF and the things that are hard to build and then could be the security issues we talked about. Are there any of these tools that depend only on existing trace points?
No.
Okay, all of them require eBPF. And
You require eBPF even if you are hooking onto trace points. But
code insertion is specific. Because
yes.
there are people who do panic about code insertion.
Yes, all of them do.
Okay.
Yeah. Okay.
You mentioned briefly that you capture the logs of files, fire them up, and make them available in the Python code above. That you said they were useful for customers to send for diagnostic. Have you actually done that with customers? Or has this been deployed in production?
So this tool is under development right now, but we have a version 1 of the tool, which is being utilized by one of our major customers for periodic log collection. But that is a very different architecture altogether.
I guess what I'm wondering is, have these logs been practically useful in determining more information about conceptual?
Not these logs exactly, but I'm sure that, so this is just a POC, right? We have a working prototype. We are planning on adding more tools that can actually, that the stuff we actually need from our customers. And I think, yes, that is going to be really helpful whenever they, yeah.
That's always the problem. We ask the customer to reproduce the problem.
Yeah.
They're head on fire.
Yep. Yeah. So sorry, yeah.
Yeah, so I had a question that you mentioned in your performance benchmark slide about memory and CPU overhead. Was there any overall end-to-end latency increase observed? I know latency increase observed in the, at least this is FIO,
Yep. Good question. So I have done statistical tests on the eBPF code, eBPF tools themselves, but not with AOD. So that is another thing I can probably do. So I have done, recorded the IO latency with and without running SMB slower and NFS slower, and I did not see any statistical difference there. But it's a good idea to run it with AOD and see if AOD, the whole construct by itself, adds any overhead. So yeah, I'll do that. I haven't done that currently. Yeah. Any other questions? Okay. Thank you so much, everyone.